Um, Good afternoon, everyone. I hope everyone is doing great. This is the last session of the day. I hope you all have a fun time learning a lot of things. My name is Anurag Jambhekar. I manage the database infrastructure team in eBay Marketplace. And I'm here with Feng, who is a principal in DBA in my team. And we are going to talk about Cassandra at eBay's scale. And before we delve into Cassandra, I just want to take a few minutes to talk about the environment, the environment we have, which basically runs all the eBay.com infrastructure. Our site is the eBay.com site predominantly runs on Oracle, and with the emergence of the NoSQL technologies, slowly we are migrating piece by piece to the newer technology where it makes sense. We started off with one Oracle database back in 1998, and now we have about hundreds of Oracle databases, which runs all the major functionalities and features of the eBay.com site. Our philosophy of running Oracle database is pretty simple, and this has helped us to basically introduce newer database technologies in the infrastructure. We can seamlessly transition from one database technology to the other technology due to the way we have designed our application and the abstraction layer. The way we run our Oracle infrastructure is that we use it as a plain data store, which provides durability and high concurrency and high throughput. And we don't use any of the true relational feature, the foreign keys and the stored procedure and all that which comes with the traditional RDBMS. Our application is predominantly read-based. We have 80% read and 20% write, and most of our reads are primary key lookup type. And so far, the Oracle layer has scaled very well for us. We have upward of about 140 billion SQL calls in a day, that runs on hundreds of Oracle server. But what we saw is that Oracle does not meet the need of every single functionality or application. One size does not fit all. And we have been introducing the newer technologies as and when we see that a use case which fits that technology. So we introduced MySQL a few years back as an alternative to Oracle. Currently, our MySQL installment is pretty small, and we run a smaller application which does not have a big storage or throughput needs on the MySQL databases. And in the last couple of years, we have been focusing a lot of our effort on introducing the NoSQL technologies. MongoDB and Cassandra being the major one in that category. So what we have found is that each technology has its pros and cons, and we evaluate that technology based on its merit, and then we see our use case. And based on that use case, we decide on which technology to use. So what we have found with the MongoDB is that MongoDB is good for very read-intensive use cases where you need thousands of reads from a single node, and where the active data set fits nicely into the memory. In that case, MongoDB scales very well, but it does have some write concurrency issues. On the other side, Cassandra fits very well for write-intensive use cases. We are using Cassandra for some of the very heavy volume write-intensive use cases, and it has scaled very well for us. And Feng is going to talk more about the deployment of Cassandra we have in eBay and how we have operationalized Cassandra into our infrastructure. And we use another product called XMP, which is another emerging database technology which offers the best of both NoSQL and traditional relational world. Currently, it's a very limited use case, and we are working with on a couple of other use cases which leverages this technology. The basic foundation of eBay database is logical host, and we divide we basically divide our application into multiple logical hosts. And the reason for doing that is to provide a transparency of the physical database layer to the application. So what we have is one physical having multiple logical hosts mapped to it. So you can think about it as a shards of an application which can map to a single physical host, or it can map to multiple databases. So this is a foundation for scaling our database infrastructure. Once we have split our application into multiple logical hosts, we can basically start off with a small number of physicals, and then as our application starts scaling, we can move this logicals across various physical without any change to the application. This transparently helps us scale our application without actually involving our developers to make any changes to the application. We also have multiple read copies where a single logical host cannot basically sustain the traffic from the application. So we have a model where you have a single write copy, and then we have multiple read copies in each of the data center to basically provide localized reads. And some of the very critical infrastructure on eBay runs with this model. And then we have our sharding, which is basically our way of actually distributing the segments of user data across multiple database hosts. And then there's a mapping which basically directs the application to the right database host. And then we do also use vertical scaling to provide the scalability where it makes sense. We periodically archive the data from our site to basically keep our OLTP data platform smaller. We have about 400 million active items on site, which is huge, and we have archival of all the items and related data on the archive database. With the emergence of the NoSQL technology, the sharding and the scalability has become easier. You can basically add the capacity, and then the software does the magic. Previously, when this was not available, we had to devise our own homegrown scalability patterns to achieve what the NoSQL solutions are basically providing natively. So as I said, logical host is a foundation of our data model where when the application is designed, we assign a logical host to it. If there is existing logical host, then it basically uses that. If not, we create a new logical host. And then we have a mapping configuration where we map this logical host to an existing physical host or to a newer physical host. This is to basically provide that abstraction of the underlying database layer to the application. And then we have our data access layer, which is called DAL layer, which does the translation of this logical host to the physical host for the application. There are many advantages of using logical host, especially in the previous world when we had a big beefy hardware and you are mapping multiple applications to the same physical. If you had that configuration hard-coded, then anytime you basically change any configuration, you have to basically make the application changes. In eBay, because of that abstraction, we have been able to freely move the logicals from physicals to physicals, and depending on the various requirements. It has also helped with the failover scenario. So there are many logicals where we have that failover functionality. So where our DAL application code, DAL application layer has that intelligence to move that traffic from a primary logical to its failover logical when the primary logical is not available. And this has provided us a lot of scalability for our read traffic, where the write host goes down but the reads continues on the failover host. And then the logical host, we are able to quickly turn off the less critical site features in the event that our demand grows our capacity projection, especially on the during the holiday traffic season. There are a couple of Sundays where we see this spike of traffic. And we do our best effort to basically project that demand and then right-size our infrastructure for that. There are certain times where we need to basically turn off less critical site feature to basically not impact the main site functionalities. So So this is the way we have designed our always available read databases. So we have a load balancer, which is a software load balancer. It's called database access layer load balancer, which basically directs the traffic to one of the many read copies of the right database. And we have in each data center we have this set of read copies. So our DAL layer, which translates that access to that logical host in each data center separately to its own localized set of read databases. And this provides a low latency read response to all the read requests from a given pool. And this is the model we have for Oracle. As you see, we have a write Oracle database, and then we have multiple read copies. But this is a general architecture which we follow for this way of scaling our reads for application where a single host cannot meet the needs of the application. When we started off with this logical host, we thought that we have broken down our functionality into smaller chunks. But we were wrong. We soon found out that even a certain logical host, we need basically capacity bigger than what is provided by a single machine. So we further broke down those logical hosts into multiple mods, and then we basically had split that into multiple mods, and then we map each mod to its set of physicals. So now we can basically split or logically split a logical host to many sub-logical hosts using this architecture. Initially, when we designed this, we started off with a mod 10. It was easier on eyes to basically find out that if a user ID ends with 0, then we basically assign it to mod 0, and if it ends with 4, it gets assigned to mod 4. But we found out that when we had to scale it, it does not provide the even scalability. We started off with 10 logical hosts, and then we split into 5 and 5 and mapped 5 to the first physical, 5 to second physical. Then we found out that now if you have split further, now we have this uneven configuration. Now we have to basically do 2, 3, 3, 2 math, or we have to do 2, 2, 2, 2, 2. So we changed that later on to mod 12, which provides us an even distribution if it starts splitting it across multiple physical hosts. But again, this has a drawback that once you have decided a mod scheme, you cannot change it later. So what if you find out that we have 12 physicals with the mod 12 approach, and then we run out of capacity on those 12 physicals? Now we cannot split it any further without making some changes to application and our data to redistribute that. So this basically, we learned some lessons from this approach of scaling our database infrastructure. And then we moved on to a range-based model. And this is the way we have split our item database, which is where when a user goes to eBay.com site and lists an item, this is the way we basically assign a particular database host to the seller who is listing that item. And then it provides us the application a mean to basically find out where that item is based on the item ID provided by the application. So in this particular scheme, we have assigned a range to the item host where we have the item host 1 basically has 10 million to 20 million item IDs, and then the item host 2 has from 20 million to 30 million, and so on. And this way, we can infinitely scale by just adding more ranges to this configuration table, and then application loading this configuration table, and then basically having that mapping in the app server. But to basically get to that host, now how do we, from a user perspective, which item host that user goes to? So we have another way of actually doing that mapping. It's something called user lookup, where we have for each user, we have a record which basically points to where that, for that particular user, where the item host is. And so when a user is, or seller is listing an item, basically application goes to this lookup table, find out that which is the item host for this particular seller, and then goes to that particular item host, and then basically use that sequence-generated ID to basically select the item ID for that item. And then with this item ID can be easily accessed from the application, because application has that mapping of all the item ID ranges. So this has scaled our item infrastructure in the last several years. We have gone from less than 200 million items to 400 million plus items in last several years, and we have never faced any of the scalability challenges or the usage challenges where our infrastructure is not able to handle the traffic. And then a large percent of our access is based on a user. That what is the items listed by a user, or what is the what are the preferences for this user, or what is the personalization data for this user. So for those type of data where the key is always the user ID, we have something called a lookup-based way of splitting our data. It's called user split, where we have this a mapping database where we have a mapping of each user to this logical host, where the defining query is always based on that user ID. So we have tens of these logical hosts where the defining key is always based on user ID, and an application goes to this user lookup database, finds out where that user is, and from there it basically goes to that DAL, basically data access layer, translate that to a physical database, and then application goes to that to query that data. And this is also infinitely scalable model, because we can basically add a new host and then basically change either migrate the data from the existing databases to this new host, or we can start creating the new users on this new host. So this is, again, another foundation for scaling our read for database infrastructure, which has gone from less than 50 billion SQL calls to 150 plus billion SQL calls in last several years. But again, all these things actually they were designed when this NoSQL options were not available, and a lot of these things actually are now natively provided by NoSQL. The way the data is distributed across multiple nodes, the mapping of the data, all that is basically natively handled by the database software itself. What are the challenges of the traditional RDBMSs? So although we use very basic features of the relational databases, we use it only to basically store data. We have simple primary key lookups. We don't use primary keys, stored procedures, functions, etc. But the volume is so huge that we sometimes pay the performance penalty of maintaining the ACID features of the relational databases. As I said, the traditional RDBMS does not have the native sharding and replication features inbuilt into it. You have to basically either get a new product or basically implement it yourself, and it's not very seamless. And then obviously the cost of the software and hardware sometimes does not justify for a use case. And then what we have seen is that we have a higher cost of commit due to the fact that the traditional RDBMS does not provide the flexibility in terms of how the data gets written from the memory to disk. And this is where I think the newer technologies like Cassandra comes into play, where we can basically, we have a lot of control over how the application interacts with the database, and a lot of control over how the database basically performs some of these basic operations. And I will have Feng talk more about the operational aspect of deploying Cassandra in the eBay's infrastructure, and then our lessons and learning from it, and then we'll have a question and answer at the end.
This one? Okay. Okay, before I really start, I want to apologize about my voice. Yesterday morning was so cold, basically I got sick, had a high fever over last night. Anyway, just want to apologize, make sure every people can hear me clearly. Before we go to the Cassandra itself, I just want about a few words about myself, about my experience. How do I get to the NoSQL world? I started with RDBMS almost more than 20 years ago. So in the beginning, when I started, that's Oracle 5. I still remember when I first time installed Oracle 5, I got about more than 20 floppy disks. It's hard. First, it takes very long for you to install it. Secondly, if you have one of the floppy went bad in the middle, you have to start over. So that's very, excuse me. That's why I still keep remembering after so many years, I still remember all these things. For past over almost a decade, I primarily work as an Oracle DBA, and also work on the Microsoft SQL Server, and also some of the MySQL stuff. As you can see, most of the time I work on the database side is all traditional database. And I also mostly work down at DoubleClick, Yahoo, and Intuit. In the last few years, when the NoSQL database become more and more popular, I realized there's a lot of new things I should learn. So basically, a couple of years ago, I joined eBay, and the primary focus, instead of the switched from the RDBMS to the NoSQL side, primarily the Cassandra and also on the Mongo side. Let's talk about why we talk about the Cassandra in the eBay. There's a few things give us a benefit, instead of the traditional RDBMS. One thing we keep hearing from the developer is they always count on the DBA to make a schema change or create a table, add a new column, before they can release their code or feature. This is not very efficient, and also as of a DBA, they always is a kind of a headache to push the schema change in the production environment. One problem we have here is, for a large system, you need application downtime to put some schema. Otherwise, you cannot get a log to release the object. Secondly, when you make changes, it's very easy to change the underneath execution plan. So that could severely impact your overall system performance. What Cassandra does is a kind of a schema-less schema. So it gives us a developer flexibility to dynamically add, change, whatever the column is there. And also for DBA, it definitely resolves one of the issues. We no longer worry about, push a schema change and cause some negative impact. Also, Cassandra-wide, based on our benchmarking, we found out it has very good performance for both read and write. Even Cassandra in the beginning was well known for the high performance writes, but in the recent releases, as you can see, based on from the compression, from the level compression, and also move a lot of objects off the Java heap space. So that gave us a lot of improvement in read as well. So later on, I'm going to show a few use cases, not just the write intensive, but also read intensive, or sometimes also for mixed workload. One thing we like Cassandra most is the horizontal linear scalability. If you think about on the Oracle side, when you're trying to scale beyond one physical machine, so we can use the Oracle rack. But the scale factor we definitely is not as linear as possible. So when you go from one node to a two-node rack, you're at best you probably can see 70% increase. If you go from 2 to 3 nodes rack, then the scale factor will reduce to 2.5 or even less. Same thing on the MySQL side, same thing on the Mongo side. So only Cassandra, from what our experience, can give us a horizontal linear scalability. That makes our life much easier, especially for capacity planning. Whenever we see the capacity increase, we can easily allocate more nodes, add more nodes to the system. And we know how many nodes we need. We know how much number you can get from the nodes. One feature also coming from Cassandra is the built-in high availability. For eBay.com kind of site, we definitely want to provide high availability in case of the machine failure or in case of data center failure. Cassandra itself, because it is a peer-to-peer architecture, first is eliminate the single point of failure. We no longer worry about a single node failure. Even node fail for like hours or days, it basically will not impact the basic functionality. Another thing is when we do the multiple data center deployment, as we always do at eBay, it gave us automatic geo load balancing. Because as you see from a previous slide, we have an application server in multiple data centers. When we have Cassandra deployed into multi data center, we always can enforce those application server when we talk to the local Cassandra nodes. That gives us very good read-write latency. You never need to go beyond same data center. So another thing is like automatic sharding. This is by nature itself, the data will randomly distributed across the multiple nodes. So you don't have to design or implement a complicated sharding on your own. Another benefit we get is for the data analytics function. Just like DataStax Enterprise, it comes with built-in Hadoop functionality and also Solr functionality. This gives us flexibility without run the MapReduce job, without build a separate Hadoop cluster. So also you can eliminate all the ETL. One feature, last feature we want to talk about is from the DB perspective. If you think about in other databases, when the data, if you have data after it expired, the only way you can do is writing some backend script to delete the data. First, you can reduce the storage usage. Secondly, you can improve the performance. But Cassandra, just using TTL, can easily implement this feature. Let's talk about the Cassandra and eBay usage. We started Cassandra about 2 years ago. We used both Apache Cassandra and also the DataStax Enterprise. When we have a project require, when the developer wants to use the analytic function, do the MapReduce job, then that's the place when we provide the DataStax Enterprise. eBay is a Java application. We are using mostly the Hector client. It's built into our common access layer, which is called the Dell Data Access Layer. So far, we have more than 10 production cluster on the Cassandra for both Cassandra and the DSE. Overall, we have more than 100 bare metal nodes. And among these nodes, we have more than 200 terabytes storage provision. In terms of the user data, we already have more than 1 terabyte across multiple data centers. For most of the data, we're in the local hard drive. But for some of the use cases which require very restricted latency, so we put those data on the SSD. Based on the different use cases requirement, we design, we implement, deploy different set of cluster. The small set of cluster we have is 6 nodes. The biggest one so far we have is 32 nodes. Here's about, the stack of the software and hardware. We're using the Cassandra over the time. We have a 1.0, 1.1, and also recently we started using 1.2. The DSE side, the one few cluster we have is the DSE 3.0. The base on the operating side, we're using the Red Hat Linux. We're using the 6.1, 6.2. The latest is the 6.3. And the Hector client, we're using 1.1. eBay, so far we haven't used the virtual machine yet because of our scale. Because it's very hard to implement such a volume of data on the VM. But for majority of them, we're using physical hardware. The first two, as you can see, we're using the HP DR380. What it has is basically just like Fed nodes. Jonathan mentioned in yesterday's keynote. Those machines are pretty powerful machines. Have a 12 core, either 96 or 128 GB RAM, and either 1.1 terabytes or 5.0 terabytes after the mirror. Regarding to the flash memory, so so far we're using the shared flash memory. Basically, we have a vendor called Violin. We're using their 6200 and 6600 flash memory array. For the smaller use cases, potentially, we are also working on a VM solution. Most of our cluster is dedicated because of their scale. We are also trying to implement some multi-tenant cluster, basically multiple applications, smaller scale applications can share a same set of hardware. This set of hardware could be bare metal, it could be the VM. Okay, I want to share some number about eBay scale, how much data we're talking about here. First thing is we have 3 data centers. For majority application, we deploy 2 data centers because that's the primary data center, our application server there. So far, production cluster, we have more than 10. We have more than 100 physical nodes. Total data size, more than 100 terabytes. The largest cluster, 32. Regarding to the transaction volume, we have more than 5 billion reads per day across these physicals. We have more than 9 billion writes per day regarding on the write traffic. The largest column family we have here is one of the logging case. We have more than 40 terabytes in single column family. One of the biggest one, largest column family per number of rows per keys is more than 32 billion keys in the single column family. The busiest column family, based on the rate, does 1.6 billion per day. In terms of the writes, the busiest column family, we are doing more than 6 billion per day, regarding on the write side. Let's talk about eBay on the deployment side. Because all the eBay machines were behind a firewall, so it's very hard for us to get the package from, for example, from DataStax RPM servers. So what we do is we build our own RPM package and put our own repository center on the server, so we can still run the YAML install, do the easy for installation and for the upgrade. We build a RPM for both Cassandra and also the DSE. They give us a very consistency. We're using the same build, same binary across all the machines. As part of the packaging, we also tune some parameter. In general, we tune a few on the kernel side and also on the Cassandra side. We're going to see in this page. There's a few examples about what we have done on the kernel level tuning and on the JVM heap side, and also on the compaction side and the Hector side. One thing I want to talk about on the compaction side is we started with the set-tiered compaction. We also tried the level compaction in the 1.08 release. But at that time, we have very bad performance issue, especially when our number of asset table grow around 200,000. So at that time, this particularly gave us one of the patch to resolve that problem. In the new 1.2 release, we're going to enable the level compression for most of the use cases. We're going to talk about a little bit about scalability. We did a lot of benchmarking. The reason we do benchmarking is we want to avoid the production surprise. You don't want to deploy a cluster, enable feature, then you realize the system cannot meet your requirement. So what we do is, before we onboard any major application, we ask the developer to run the load and performance testing in the pre-production environment, which we have also a node cluster. So from this load LNP testing, we can easily to project whether how many nodes we need to support the user traffic. In general, for the Cassandra, most people think, okay, it's very easy to scale by scale out. When you see the traffic increase, what it does is just add more nodes. For us use cases, sometimes we do find the issue, in some cases, we should do the scale up first. One example we saw is network saturation. Machine we start with early only have a single gig network card. Instead of add more physical nodes, which is more expensive than 10 gig network card, what we do is we replace the machine with a different machine have a 10 gig network card. So instead of purchasing more expensive physical nodes, we can easily to increase the network traffic by around $1,000 instead of $10,000. Also, we can easily to solve the error latency problem instead of split the traffic across more nodes. We can also replace the local storage with flash memory. So far, we really, because of the machine we have so powerful, regarding to the CPU core, regarding to memory, we haven't really seen any bottleneck in these two areas. But maybe we'll see from the VM solution. Few notes on the operation side. Because a lot of the use cases is read-only logging. So in that case, we don't run the routine repair. As most people know, that repair is a very error-intensive operation. Only we run the repair once when a machine down for whatever reason for more than hand off the window. In that case, when we bring machine up, we run the repair, make sure we can get the missed data from the remaining nodes. We use, in terms of the client configuration, we don't give them an actual physical host name. What we do is we're using Cname. This Cname can easily transfer between the physicals. What the benefit for doing this is when the machine gets replaced, normally it gets a different IP address, gets a different host name. With the Cname, we can easily move the Cname from existing one to the new one and without changing client-side configuration. This is one of the benefits. Regarding to the TTL data, one issue we had early is when we do the capacity planning, we didn't include the GC grace in the beginning. For example, especially for the data with the short TTL. One problem we have early is we have a use case with 7-day TTL. We keep seeing the data increasing beyond our initial projection. Later on, we realize for the GC grace period default 10 days, that means we are actually store 17 days of data instead of 7. So if you have a similar case, you need to, when you do the capacity planning, either you need to reduce the GC grace period or you just had to add more storage. One thing we did on the memory side is we don't use a swap. Because if the machine keeps doing the swapping, it makes the machine kind of an unstable state. In Cassandra world, in this case, it's better take a node down, so other nodes can continue function well. Another issue we see before is bootstrapping. Most of the time, whenever we add a new node, or replacement, we do the bootstrapping. A few of the time we realized bootstrapping didn't work. First time didn't work, second time, then we have to keep trying it until it succeeds. So if you ever have this case, just try a few more times, it will work. Regarding the row cache, most people already know row cache only works for a very small data set. If you have more than 100K rows or even a bigger set exceed few hundred GB, row cache does not work. For eBay use cases, we always disable row cache because of the data set. A few on the operation side, monitoring is very important for the production system. We have multiple ways to monitor Cassandra. First, we integrate with our network operation center, which is operates from both US and China, 7/24. We integrate Cassandra with this log along with Oracle, MySQL, MongoDB together. This is the first tier. Whenever there's a problem, the tool itself will collect the Cassandra status up or down in almost real time. Every few seconds, it queries Cassandra nodes. we write our own customized small HTTP server. So it pings the HTTP daemon every few seconds to see it's Cassandra up or down. So if a machine ever have a problem in a few seconds, you're going to notice on the log screen. I'll show you in a few minutes. We also, for the low latent priority events, non-critical one, we also have a self-developed email alerts for the pending compaction, garbage collection, frequency, etc. We also use the DataStax enterprise, Center enterprise. First thing we can see have a high-level dashboard for more than one cluster at the same time in one place. Second thing is we also use it for certain administration operation. For example, do a rolling restart. It's very convenient. This is a screenshot of the next Op Center. I have to mash up a few the number of nodes or stuff, the name. This is our log real-time monitoring. So this is only the Cassandra side screen. In the real world, it can also show the Oracle, MySQL stuff. So this can easily map from one of the Cassandra physical nodes to one of the Cassandra nodes to actually physical host and about the load average and the sessions. So when the one machine have a performance problem, it starts at the yellow on the top, which means Cassandra still function, but it take a longer time to ping the Cassandra. Second case is if a machine is down, so the machine will pop up on top as red color. That means I couldn't connect to the Cassandra nodes from here. Just a few use cases on the eBay. We have a really intensive metric use cases, logging, metric collection. We also have a really intensive, we call it recommendation backend. These two I'll go over in the next few slides. We also have a mixed workload is coming to the production, we call it personalization. Here's a screenshot for metric collection. Basically, what it does is storing and serving real-time metrics from tens of thousands of eBay devices. That include server, switch, storage array, etc. Those can be used for the dashboard reporting and also the triage automation. For this particular cluster, it has a 16 node 1.22. And we only have 2 copies of data across 2 data centers. The reason we cannot, most cases we have 2 copies is because of data size. And for this particular case, we have more than 600 million keys. And every day, this is the most write-intensive case. It does more than 6 billion writes, including they also do the roll-up within the Cassandra. This is a really intensive case we call the recommendation backend. eBay, we have more than a few hundred million users, and also every day there are several hundred millions items listed. And every day there's a lot of billions user activity. For example, when you bid an item, when you watch an item, when you actually buy an item, all these translate to an event at the backend. So what it does basically is this is the recommendation that is based on the user past activity to predict what you may like in the future next. So if you go to the eBay website, sometimes you're going to see item you may like. That's all coming from this kind of system. For these use cases, we have 2 different clusters. One have 32 nodes, another one have 8 nodes. So totally, we have 40 nodes combined. Overall, within this cluster, we have more than 25 billion keys, and we have 32 terabytes SSD because of the very read intensive. They have a high requirement on the read latency. This is about 600 million writes per day, about 3 billion reads per day. Last thing I want to talk about is the vendor support. It's very critical for a company like eBay side to have a good partner when we adopt a new technology. We're very thankful to have DataStax as a partner when we start using the Cassandra. In the past few years, we want to thank the DataStax service team. They always give, when we ever open the use cases, they always give very good services, provide a solution, or either provide a workaround. There are a few cases that we have seen before, and also it becomes actually either a bug or to be an enhancement feature for the next release. Yeah, just like you said, even the support contract costs money, but if trust me, money is not really wasted. Looking forward, a few things we want to do is we want to go beyond the reading intention use case. We want to do the more critical feature, move more critical feature, just like personalization, anti-fraud, into the Cassandra platform. Another thing we want to do is hardware virtualization. We have an internal called OpenSpreaders. Is a VM infrastructure. It's built on top of the OpenStack. Where next we'll see how can we leverage the VM platform. Another factor we want to scale better is separate storage from the compute nodes. This gives us more flexibility to scale a particular component, especially for the storage-wise. We don't have to decide the number of nodes based on the storage anymore. We want to do more automations. We want to do more like a self-serve model. Just like a PD, right now we're DBA install the deployed cluster so PD can use. Going forward, we want the PD can have click a few buttons in a few minutes, maybe hours, you're going to have a ready-to-use cluster. We also want to basically have a more runbook kind of a practice so we can leverage knowledge across the different teams. This will kind of wrap up for our presentation. If you have any Q&A, we can probably be here for a few more minutes. You can ask any questions. We want to thank your time, and also eBay always looking for the NoSQL talent. So if anybody have interest to work on the big data, as we showed the size of data here, feel free to send your resume to Anurag. Here's his email address. Anybody have any questions? Now we can answer for Q&A session. All right, thanks.
Thank you for your time, guys. Have a wonderful evening.